Hello everyone. So in this video I'm going to discuss analysis of a full bridge diode rectifier. This is a specific case of a full bridge diode rectifier that you actually have a center tap secondary transformer, and you will see by the end of this discussion why as this specific configuration is useful and how you can use it. So the input is applied to the primary, and then obviously it's a sinusoidal voltage, and the secondary has three terminals, and one of the terminals connects to the middle of the secondary winding, and therefore you get two sinusoidal voltages in the output, assuming that you take the middle as your reference. Then these two are going to be exactly equal to each other the way that it's defined here. So it goes positive, negative, and then positive, negative. In other words, this voltage is higher than the ground, and then the ground is higher than the voltage on the bottom, and you get two equal voltages at any point of time. And this is critical to understand. And as we go, we're going to discuss this in more detail. So I've already have some of the waveforms drawn here, and as we go through it, you're going to understand more about why they look the way they do. Let's start with the first lobe of the waveform. I'll use red for that. So I'm going to focus on this first lobe where the voltage of the positive terminal for both of these is actually higher than the voltage of the negative terminal, which means that the positive terminal here is higher than the ground, and then the ground is higher than the negative terminal right here. Now, you have to keep in mind, and this was the discussion that we had before, and I'm going to repeat this, there are two things that are important, and this is my suggestion for better understanding circuits like this, is to focus on current as opposed to voltage, focusing on voltage first, and then once you understand the flow of current in the circuit, you can go back and look at the voltages. This is useful when you have diodes, because you know when the diode passes current, it's on, and when it doesn't pass current, it's off, and based on that you can then simplify the analysis. Basically turn the diode into either a short or an open in an ideal case. Okay, so given that, then the next thing that we have to pay attention to is that once the potential of a node is higher than the potential of a different node, the current, if there would be any current flow, would go from higher potential to lower. So for this first lobe, we said that the potential of this node is higher than the mid tap of this of the circuit, which is our reference. Therefore the current actually is going to go out and then come back and go to the ground, and these two are the same. So basically the current has to go here and then somehow end up into the ground there. These two nodes are the same. So now let's follow this and see what happens. We get to this node, and then there are two paths, but then obviously this diode can't let the current pass, so there's really one path for the current to go. And then we get to this, and then same thing happens, so the current goes here and then it goes through the resistor. So for this positive lobe and for the top portion of the secondary, the current path, the possible current path is like this. Okay, and then it ends up in the ground, which is where we wanted it to end up, and that's a possibility, and this is going to happen assuming that there's enough voltage to turn the diode on, meaning that if the voltage goes anything beyond the built-in voltage of the diode, this is going to happen. Now for the bottom half of the transformer, what's going to happen is that, as we mentioned, this time again, the potential of the positive terminal is still higher than the potential of the negative terminal. They're the same thing happening for both of them. So if Vs is positive here, Vs is positive here, which means that for this one now current has to go from ground to this node right here. So the direction of current for that one has to come from ground and end up in the negative. So it has to go pass through the resistor and then comes here and gets to this. Now there are two ways for the current to pass, but you have to notice that for this diode, the potential on the cathode side is actually, with respect to ground, is a positive voltage. We already said that. So this is higher than ground. Now, for the anode side of this diode right here, the focus is that diode. What's happening is that the voltage, the current is passing, it starts from ground and passes through resistor. So it's actually lower than the ground. This is higher than the ground. This is lower than the ground. In other words, this is higher than this. So the cathode is higher than the anode. And therefore that diode can turn on. But this diode would turn on because this node actually has the lowest potential. So there's current passing here and then going back to there. So there are two paths for the current in the same loop. One from the positive terminal of the top half of the transformer all the way to ground, and then the other one from the ground all the way to the negative. So in reality what really happens is that the current, because these two currents are actually equal to each other, so this current continues to come, because these two are, now we know are equal to each other, continue to go like that. So the loop for the current goes like this and then all the way back to negative. Really there's no, because like this is not, these two are just connected to each other. And the ground is not an actual terminal. The ground is just a convention for us to say this is 0 volts. So this is how the current is passing through the whole circuit. So now once we settle that, then we can go and start drawing the voltage of the V plus node and V out plus and V out minus, and knowing that the diode is going to turn on as soon as there's enough voltage that turns the diode on, which is equal to the built-in voltage of the diode. If you assume the diode is ideal, then as soon as Vs becomes positive, the diode turns on, and then V out is going to just follow Vs. So I would have drawn something exactly equal, the same as the blue down here for V out plus. But now, if you're assuming that there's a drop of voltage equal to V gamma, the built-in voltage, then the peak is equal to Vs minus V gamma, and the diode only turns on after the input voltage reaches the V gamma. So this is what you're going to see for V plus. And now for V minus, I'm using a different color to show that the green, now green is with respect to ground, green is right here basically, and this is how the voltage, the green is right here, and you can see that when the voltage Vs is positive, the voltage here with respect to ground is negative and equal to that voltage that you see on top. It's basically because you assumed your ground is right in the middle. So that said, therefore the same thing is going to happen for V out negative, but this time the difference between this node and V out negative is across the diode, and the voltage V out minus is this time higher than the voltage of the green node for the amount equal to the built-in voltage, which means that the voltage goes down to the value of Vs plus V gamma, minus Vs plus V gamma. So you get minus Vs plus V gamma for the negative peak and Vs minus V gamma for the positive peak. So that settles what happens for the first half, for first lobe or positive lobe of Vs. Now we can move on to the negative lobe. I'm going to remove all the red and then come back and discuss the negative lobe momentarily. Okay, so now for the negative lobe, I'm going to use purple. Now this time the voltage right here goes below ground, and the voltage right here also goes below this one, which is the same thing as saying the voltage right here goes above ground, right? So therefore the current this time has to actually go from ground, for the top half has to go from ground to the positive terminal right there, or that's not the terminal with the plus sign right there. So the current has to go like this, and as you can see, if it goes here, there's no path for it to go. So this time the current actually goes here, and then here, and then passes through this diode, and then right here. So this is the path for the top one, and then for the bottom one, this one is higher, so this time the current goes out of this one, so the opposite of that happens here, goes there, and then to ground. So these two have switched, and as a result what's happening is that these two diodes are this time on, and these two that used to be on are now off. So the diodes that are on have switched. But one thing that you can notice here is that the direction of the current passing through the two resistors haven't changed. So both of them still pass current in the same direction. So therefore the voltage for them, Vout plus and Vout minus, are going to look the same as what it was before. So Vout plus, again, I'm going to continue with red for Vout plus, is going to exactly do the same thing that it was doing before. And Vout minus is going to do exactly the same that it was doing before with respect to ground. And that concludes our analysis. Now you can see what happens here. If I replace R's with capacitor and look at, so if I put two capacitors instead of the resistors, I put two capacitors here. The red waveform is going to get rectified, and you get a constant voltage for V plus, which is a positive voltage, and for the green you're going to get a negative voltage, a constant negative voltage. So with this configuration you can actually get two complementary DC voltages, and that's why this is called a complementary full bridge rectifier. And it's very useful. A lot of times in electronics you need both the positive DC voltage and the negative DC voltage. So again, if I replace the resistors with capacitors, these are the waveforms that I'm going to get. This charges up, goes up there, and gives you a DC voltage on top. And then for the negative, let me just use a different color if I can. And that would be like that, and then constant. Well, I didn't do a very good job for the blue one. It's going to be passing through the positive peak of all of these. Now obviously if you start putting the resistor back, this is going to do the same thing that we discussed. The voltage is going to drop and then charges back up, drops, charges back up, and you're going to get a ripple if you have both a resistor and a capacitor. So in that case, this goes up and then down, then up, then down, then up, and it keeps going on. And the same thing for the negative one. Okay, hopefully this has been helpful. Thank you for your attention. I'm going to close this